We just discuss two additional properties of the Fourier series. Suppose we have a function f1 of t and its Fourier series is this with cn1 as the coefficients. Now, if this function f of t is shifted in time, translated in time by a certain amount, let us say f1 t minus tau. So, it is the same function, but the origin is shifted. It is delayed by an amount equal to tau seconds. Then it can be shown that the corresponding Fourier series for this will be such that cn2 is cn1 multiplied by e to the power of minus jn omega naught tau, which immediately shows that the magnitude of cn2 is the same as the magnitude of cn1. However, the phase is different, the angle is different, which means that the magnitude spectrum of f1 of t and the magnitude spectrum of f1 of t minus tau will be the same. The phase, however, is decreased by an amount proportional to the frequency. An example of this we have seen earlier when we took a square wave with the origin at two different places, and you could express a square wave in terms of cosine functions or sine functions. So, this is an important property that the constitution of the various harmonic components, the proportions of the various harmonic components will not depend upon where you place the origin. A second property relates to, suppose you have a periodic function, you multiply by a sinusoid. Again, let f of t be the periodic function. And let this be the Fourier series for that. The spectrum for this is C naught, C1, C2, C minus 1, C minus 2, etc. Now, what I would like to ask is, if f of t is multiplied by cosine omega c t, then we can say this is, after all, cosine omega c t is e to the power of j omega c t plus e to the power of minus j omega c t divided by 2, and you multiply this by Cn e to the power of Jn omega naught t. The result is you get one expansion Cn upon 2 e to the power of Jn omega naught. I may as well write this omega c plus omega n omega naught, omega c plus n omega naught t, plus another group of terms Cn by 2 e to the power of minus j omega c minus n omega naught. So, you have frequencies omega c plus or plus n omega naught, where n ranges of course from minus infinity to plus infinity, and another set of terms frequencies omega c minus omega c minus n omega naught. So, in other words, if you look at the spectrum here, centered around omega c, you have various harmonic components. This will be C naught by 2, this is C1 upon 2, etc. And centered around minus omega c, you have a second set of components. This is again C naught upon 2. So, this portion corresponds to this, and this portion corresponds to this. So, what it means is the spectrum gets divided into two parts. One part is shifted to omega c, another part is shifted to minus omega c. Instead of being centered around the origin, it is centered around plus omega c and minus omega c. This is done in communication and instrumentation. When you want the information content of a signal, instead of being centered around the DC value, you would like to be shifted to a more convenient frequency for purposes of instrumentation or communication, and in that context this is said to be the carrier frequency because it carries the information content associated with f of t. You can use this to use this information. As an example, you can think of, if you have a full wave rectified sine wave, you can think of this as the product of a sine term and a product of and a square wave. Suppose you multiply these two out, you can get this. Therefore, to find the Fourier series for this, you can use this property and then find the Fourier series. I will leave this as an exercise for you. To sum up, we have discussed at length the various properties of Fourier series, how the series can be obtained, the characteristics of the series, and how it may be used to analyze circuits excited by periodic but non-sinusoidal waveforms. We derived analytical expressions for calculating the various harmonic components. This is a process which is referred to as harmonic analysis. If the function f of t is given in the form of analytical expression, we can carry out this harmonic analysis analytically in the way we have done in the various examples. However, if the function is available in a graphical form with no analytical expression on hand available to you, then we can use numerical methods. And computers can also be used, software programs can be developed to give the various harmonic components once you have the waveform prescribed, or it can even be captured by means of discrete data points experimentally. We also have instruments available to do this harmonic analysis. There are two categories of instruments. One is called the Harmonic Analyzer, where you feed the signal to the Harmonic Analyzer and you tune it and get the amplitude or magnitude of each harmonic component one at a time and read it out on a meter. The other class of instruments are known as spectrum analyzers, where if you feed the signal, you will find the entire magnitude spectrum displayed on a screen. This is called a spectrum analyzer. The ideas of Fourier series or the harmonic analysis of periodic signals can be carried over to signals which are not periodic. They are called aperiodic signals. And this is a subject which we will take up next when we talk about the Fourier integral concept. With this, we conclude our discussion of the Fourier series. In the next presentation, I will give you a set of examples as an exercise for you, and also will also include a elaborated demonstration on some of the concepts we have discussed.